Welcome to our presentation. We are the Linear Mappers, consisting of a team of six: Andrew, Jason, Johan, Lazar, and Yaniel, and myself, Ijlal. We are going to be talking about K-maps and the benefits of using K-maps. So let's move on. What are we going to be covering in this presentation? We're going to be covering K-maps, the history of K-maps, the real-world use of circuit design, and how there are different methods of deriving Boolean expressions. We're going to talk about the conventional methods, and then we're going to talk about how, if we use linear algebra, how those methods are much better in, finding Boolean expressions.
On a journey through the history of Karnaugh maps, a pivotal tool in digital circuit design. Our story begins in 1953 when Maurice Karnaugh, a bright student at MIT, presented the world with his revolutionary method in his master thesis titled The Map Method for Synthesis of Combinational Logic Circuit. Before Karnaugh maps emerged, simplifying Boolean expression was akin to navigating a complex maze. Engineers and mathematicians grappled with intricate algebraic manipulations to process both time-consuming and prone to error. It was in this challenging landscape that Maurice Karnaugh's innovation shone. In his quest to simplify Boolean expressions, which serve as a mathematical backbone of logical functions, Karnaugh introduced a radical shift. His approach was just a method, it was a paradigm shift, offering a visual and systematic route through the intricacies of logical simplification. Let's dive into the heart of Karnaugh maps. Imagine them as a graphical representation of a truth table, the blueprint that defines the behavioral of a logical function. These truth tables are just transposed into two-dimensional matrices, creating what we call Karnaugh map. In essence, Karnaugh maps provide a bird's-eye view, allowing us to see patterns and streamline logic in a way that wasn't possible with traditional methods. It's the difference between deciphering a tangled web and having a clear map to navigate through the complexities of digital circuit design.
Let's talk about circuit design and its application in the real world. So why do we care about circuit design? Circuit design is one of the key factors in the age of technology, as it allows for the continued improvement of the devices that we use every day. These improvements mainly come from the minimization of circuits, as they bring significant advantages, including complexity, as less components in a circuit reduce their overall size, and it also decreases their time for assembly. Efficiency, as a fewer number of elements produce less operation delay in the functionality of the circuit, as well as increased durability due to less power being required. And lastly, cost, as a reduced circuit with less components requires less resources to implement, and thus less equipment to maintain. These three elements are closely related to an important concept called Moore's Law, which further shows that constant work in circuit design has a correlation with a trend in which the density of transistors doubles every year, meaning that with each iteration, the same number of components will fit in a smaller space. Now let's present the problem. In this presentation, we will be going over the process of implementing an optimized circuit, in which we must know how to derive the expressions that we need, how to optimize the expressions obtained, as well as how to build the circuit with the resulting expression.
Now we will move on to Boolean algebra and how it relates to circuit design. The binary system, the way in which you represent binary numbers, is at the core of digital circuit design. The system consists of zeros and ones, where each digit represents a state in a circuit. Essentially, these values are used to represent the current flow in the system. We can think of these binary numbers as switches for the circuits, where a 1 indicates true or on, while a 0 indicates a false or off state. To apply this logic into circuit inputs is very simple. When the input of a circuit receives a 1, this indicates input is active or on. Conversely, a 0 shows that the input is off or in an inactive state. Now that we've covered the basics of binary numbers, we can see a more visual representation of the values by looking at various logic gates and their truth tables. For example, if we look at the AND gate in its truth table, it outputs a 1 only when both of its inputs are a 1. In all other cases, it will output a 0. The OR gate outputs a 1 when at least one of its inputs is a 1. Next, we see the NOT gate, also called an inverter, simply flips input. If it's a 1, it outputs a 0, and vice versa. Lastly, the XOR gate, or an exclusive OR, outputs 1 only when its inputs are different. Otherwise, it outputs a 0. Understanding how to convert Boolean expressions into the respective truth tables and logic gates is a crucial part of circuit design.
Now, how is it we derive a Boolean expression from a truth table? Well, any given truth table, the number of rows are dictated by the number of variables given. So if an expression has 3 variables, it is 2 to the power of 3, meaning 8 rows, as shown below. It is going to contain all possible input combinations from number 0 all the way up to 1 less of the number of rows it has. So in this case, 7. What we have to do is just go ahead and put in all the values where f, meaning the function, is outputting a 1. So we put that in the truth table. Wherever 1 is in the table is dependent upon the behavior of the circuit. So this can be random dependent upon the expression we're given. So in this case, we take the values where they're 1 and we transition them over to an expression as shown there, where it's f equals the given expression.
Process for doing Boolean simplification is using Boolean identities. As you can see, there are numerous identities that can be used that helps in the process of simplifying Boolean expressions. The issue with this is that there can be a lot of error reductions that can take place. Secondly, using K-maps allows you to find patterns, whereas using Boolean identities doesn't. So are there other ways, and can linear algebra help us make this process faster? Let's go through the step-by-step process of using K-maps for Boolean simplification.
So as showcased before, we were able to, of course, use the Boolean identities to simplify this expression from this truth table in a longer process where we had to go, term by term, find the common factors, similar to math. But in this case, because it is Boolean algebra and it's mainly focused on the simplification of identities, we are also able to use linear algebra in an indirect way. It can be used by actually drawing matrices as above. And we're about to show how we're going to, of course, fill the variables in and simplify them. But the size of the matrix in which we draw is all dependent on the size of the actual Boolean expression. So to further explain, because we have 3 variables, x, y, and z, 2 to the power of 3 means we need 8 cells. So a 2 by 4 matrix will do as above. So what we're going to do is we're going to punch in the values from the truth tables. So f is a 1 when x, y, and z are all 0. So right here, 1. It's a 1 when it's 0, 1, 0, as shown here. It's also a 1 at 1, 0, 1, 1, 1, 0, 1, 1, 1. Now, when we then have this diagram here, it's important that we take a step back and keep in mind these rules here of grouping, because we can't just group however we feel. So, for example, we have this one and this one here. We can't do a diagonal grouping as such because it's just not allowed. We also have to group in powers of 2, so we can't group these 3. It has to be either 2, 4, 8, 16, whatever size we can. And we can also do overlapping, and I'll show how that looks. So I'll just start off with the overlapping because it's not as easy to see. But if we look at this guy and this guy, you would think that there are no adjacent cells to it, but actually there are. So you can do this group here, and it wraps around. And what we want to do is, as we group them, we're going to want to start writing out the terms. So here we have x naught, and then we have z naught. Reason why is because we're simply focused on this row where x is a 0. So as you recall before, we denoted any zeros as a prime. And then if we focus on here, well, z stays 0, 0, as you can tell, the rightmost bit. The leftmost bit is, of course, corresponding with the y, which changed from 0 to 1. So if we ever see that a variable's bit changes from 1 to 0 or 0 to 1, we discard it because we look at it as redundant. So we don't have to worry about writing it again. So then we say a plus because now we're going to group another term. So again, we can't group these 3, so we're going to have to divide them into 2 different groupings. So we're going to be able to do this group here, which is going to be an x. And then, well, z stays a 1, but y changes from 0 to 1. So we're going to put z and then plus. And then here, similarly, we get this grouping here, which is still x. And then now in this particular situation, y remains 1, but z changes from 1 to 0, so we don't write that. So we have this. And as shown before, this will be the simplest Boolean expression here, and it was done much, much easier with a K-map. This process is way much more applicable when we have 4 variables and even 5 and 6 variable K-maps, because it can get very big, and writing everything out and kind of paying attention to the identities is very error prone, and it just makes the process much more efficient that way.
Let's take a look at the circuit diagram. Using the same simplified Boolean expression as before, we can now design the circuit using logic gates and wires from inputs x, y, and z. We can see now that there are less gates in the circuit. Let us look at the decoder implementation. Alternatively, linear algebra can be used to illustrate the same circuit but using an integrated circuit called a binary decoder. The output of a decoder implements an identity matrix as shown below. To showcase this implementation, we can take the same truth table of the Boolean expression we used to simplify earlier. Whenever a value of 1 appears in the truth table, we draw a wire from the respective values connecting the decoder to an OR gate. In conclusion, the application of linear algebraic techniques such as Boolean matrices, truth tables, and K-maps in simplifying complex circuits stands as a testament to the transformative power of mathematical tools within the realm of computing. This journey of simplification and optimization not only enhances circuit efficiency, but also embodies the ongoing pursuit of innovation and improvement in the field of technology, enabling us to convert abstract concepts into practical and efficient circuitry while minimizing costs and maximizing resource utilization.
These are the contributions for this presentation and project.
If you want to test the circuit for yourself, here are the steps to access it online.
These are the references that have been used for the project and presentation.
Thank you for listening to our presentation.